So a natural question in geometric measure theory is what happens to the Hausdorff dimension of sets under different transformations. And a very natural operation that we can study are orthogonal projections. So first, recall from our discussion on Hausdorff dimension, we saw that any Lipschitz map does not increase the dimension of a set. And since orthogonal projections are Lipschitz functions, that means that they do not increase dimension. However, they can decrease dimension, and quite substantially. So for example, recall the four-corner Cantor set. So this was a set that we got by taking the unit square and contracting it by a factor 1/4 to each one of the four corners and making 4 copies of itself and then repeating this process. So the dimension of this set was equal to 1. However, notice that by the structure of the set, if I project this set into the real line down here, then the resulting set that I get is going to be another Cantor set where instead of moving the middle third, for example, I'm moving the middle a half over and over again. And so then you can show that the dimension of this set is in fact equal to 1/2. Now, even though the projection can be strictly less in dimension than that of the original set, the following result says that if we're projecting into a vector space of larger dimension, then this is actually a rare event. So specifically, given a Borel set A and a dimension M bigger than the dimension of A, then for almost every m-dimensional plane, the projection of A into this plane preserves the dimension. Okay, so we'll go over the proof. So notice that we really only have to show this inequality, since the previous result says that the opposite inequality holds always. Now we're going to need the following estimate from our discussion about Grassmannian measures. So just keep that in mind as we go through the proof. So let's let S be some number strictly less than dimension of A. Now recall from our discussion of energies that the dimension of A is the same thing as the supremum over all numbers S for which there exists a measure of finite S energy supported on my set. So because S is less than this dimension, this implies that there exists mu in M of A. So recall there's a set of measures of positive finite measures supported in my set such that the S measure of mu is less than infinity. Okay, so now let's consider the following integral. So I'm going to look at the average S energy of the push forward measures of my measure mu and integrating with respect to the Grassmannian. And I remove the subscripts here because we know what the dimensions are. Okay, so let's write this out. The same thing as the triple integral of x minus y to the minus s d pi v mu of x d pi v mu of y d gamma of v. Now recall from our discussion of push forward measures that when integrating with respect to a push forward, that's the same thing as just integrating our function composed with the function we're using in our push forward. So we can actually pull these projections into our integrand. So this is the same thing as this triple integral of pi v of x minus pi v of y minus s d mu of x d mu of y d gamma of v. Okay, so now I'm going to rearrange this integral slightly. I'm going to pull the gamma integral inside. So this is the same thing as the double interval of the integral. So notice that the projection is linear, so that means that I can just combine these two terms into one. So it's the same thing as pi v of x minus y to the minus s d gamma of v, and then d mu of x d mu of y. Okay, so now we can use this estimate up here, right? And remember that this works exactly when I have a dimension S that is strictly less than M, the dimension of the plane the planes I'm projecting into. And so I apply this lemma So I get that this is at most some constant times the double integral of x minus y to the minus s d mu of x d mu of y. However, this is just the s energy of my original measure, which is less than infinity. So thus, this implies, so for almost every plane V, the S energy of this projected measure is finite, which implies that pi V, which implies that the dimension of the projection of these measures is at least the number S. And from here, it's not too hard to show that letting S go up to the dimension of A, that in fact for almost every plane V, that the orthogonal projections have dimension at least the dimension of A. Now, if we have a set A of dimensions strictly bigger than M and we project it into a M-dimensional subspace, then yes, the dimension is going to drop, but what ends up happening is that the Lebesgue measure of the projected set is going to be positive for almost every plane V. So in order to prove this theorem, we're going to require another estimate on the Grassmannian measure, which I record here for reference. Okay, so let's first observe that because M is strictly less than dimension of A, that implies that there exists a measure mu in M of A, so it's positive and finite measure, such that N is supported in A, such that its M energy is finite. Now, if we want to show that the projection of a set has positive Lebesgue measure, so I'll write bar around the set for short for Lebesgue measure. So this is positive if we can show that the push forward measure is absolutely continuous with respect to Hausdorff measure restricted to this plane. So the reason why is because since mu gives positive measure for the set A, its push forward is going to give positive measure for the projection of A, and by absolute continuity, that will mean that this measure will give positive Hausdorff measure for that set as well. Now, absolute continuity follows if we can show that the lower derivative of pi mu with respect to m-dimensional Hausdorff measure restricted to the plane is finite for pi v mu almost every x in the plane. So you'll recall this theorem from our discussion of differentiation of measures. Okay, so that means that our goal now is to show that for almost every plane v and for pi v mu almost every x in that plane, that this density is finite. And we'll write just d lower bar for short for this function. Okay, so one way that we can show that is by just looking at this double integral of the lower derivative with respect to d pi v push forward mu of x and d gamma of v. So we want to show that this integral is finite, and then that will prove that for almost every v and pi v mu almost every x, this lower derivative is finite, and then we'll be done. Okay, so recall that this is the same thing as lim inf as delta goes to 0 of pi v push forward mu of this ball, center x of radius delta, over the Hausdorff M measure restricted to the plane of the same ball, d pi v mu d gamma v. Okay, so a couple observations here. So by Fatou's lemma, we can pull that lim inf out. Okay, and so that was by Fatou. Okay, now second thing, we know
exactly what the m-dimensional Hausdorff measure of a ball of radius delta is. It's just the diameter of that ball to the power m. So that means that we can factor out, so I'll rewrite it down here, the same thing as lim inf as delta goes to 0 of 2 delta to the minus m times the integral of the pi v mu measure of this ball, which I'm going to rewrite as the measure of the projection of the inverse projection of this ball. Okay, so that's the definition of push forward measure of a set. D pi v mu of x d gamma v. And of course, also I need to replace this d pi mu over here with just d mu. So let me move this back over. There we go. Okay. Now, one thing that I observe is that this is a double integral of measure mu of a set. So I can also think of that as a triple integral of a characteristic function, right? Because the measure of this set, the mu measure of this set is the same thing as integrating the characteristic function of the set with respect to mu, which means that I can do Fubini's theorem and interchange the order of integration. So in particular, what I'm going to do is I'm going to replace this mu with the gamma over here. So now I'm going to take the gamma measure of not the set of y's, but the set of v's, and then I'm going to integrate d mu with respect to y. All right, and so that follows by Fubini's theorem. And now by the lemma up here, I can bound the gamma measure of this set here. So this is going to be at most lim inf as delta goes to 0 of 2 delta to the minus m times the double integral. So this is going to be, let me write this out in full, delta to the m divided by x minus y to the m, d mu of x, d mu of y. Now notice that now I have a delta to the m here and another delta to the m there. So these two deltas are going to just cancel each other. And now this integral here is constant, so the lim inf actually is just constant, so obviously converges. And what I have remaining is just a constant times the double integral of 1 over x minus y to the m, d mu x, d mu y. But that is exactly the m energy of the measure mu, which we're assuming is finite. So thus, we have shown that this integral right here is finite, and thus for almost every v and almost every x in the plane v, this lower density here is finite, and that implies that for almost every v, we have absolute continuity of the push-forward measure of mu with respect to Hausdorff measure of the plane, and that implies that the projection has positive measure.
So in this lecture, we covered results that said, given a set A of a certain dimension and given a set of planes of a certain dimension, that the orthogonal projection of A into those planes satisfied a certain property outside a set of Grassmannian measure 0. Now, one thing that we didn't study was whether the set of exceptional planes was smaller than just Grassmannian measure 0. Do they have very small Hausdorff dimension? So there are some results that actually give better estimates on the dimension of the sets of exceptional projections, and I'll leave the theorem up here. We're not going to go into it in this course since we'd have to review a lot of Fourier analysis. But if you're interested, you should take a look at the book by Pertti Mattila called Fourier Analysis in Hausdorff Dimension. And in fact, one of the reasons why energies are so important for estimating Hausdorff dimension is that they play very well with the Fourier transform. And so actually that book gives a good overview of a very rich subject of how to apply the Fourier transform to study Hausdorff dimension in other applications, not just studying Hausdorff dimensions of projections of sets.